Good afternoon. It's Saturday, June 24th, 2023, and it's a pretty nice afternoon, late afternoon, early evening. Being in a pretty farther north city, when the days get long in the summertime, they get very long, or they're about 14-hour days at least. I suppose it's about 5:30 a.m. to about 9 or 10. It's quite north. But anyways, yesterday there was kind of the discussion about trying to get in and understand the geometric and arithmetic means. And so this is kind of inspired by things like the midpoint theorem and the intermediate value theorem with respect to things like L'Hopital's rule and Rolle's theorem. And the idea is trying to figure out what it means when things are stacked together like a house of cards of sorts. What are the little ramps between connecting all these things, and how are the angles and this and that kind of stuff. So fairly, that's kind of what it's about. And so one thing I was studying a bit yesterday was in a book of Goedel's theorem. So it's Ernst and Nagel's book on Goedel's theorem. And what it has is it has one of the diagrams of what's called Pappus's theorem. And so Pappus, P-A-P-P-U-S, Pappus, was in the era of the Greek geometers or antiquity, from what I understand. And basically Pappus's theorem is like this. Draw three lines across the page. And basically the idea is that they don't cross in the region under consideration. And so mark any 3 points on the top line and any 3 points on the bottom line, and the middle line, or rather, when you have those 3 points on the top line and the bottom line, and you connect all them, each one of the one on the top line to each one of the one on the bottom line, the points where they cross, be on, they make the middle line. And so it's just an interesting theorem about how there's those 3 crossings in the middle. So it's kind of got the shape of a Kuratowski graph, which is kind of like a row of things on the left and a row of things on the right, and then each one of the ones on the left is connected to all the other ones on the right, K3, say, in the language of graph theory, or where that lives. But what was just kind of remarkable about it is there was the discussion yesterday of the quadratic sieve, and this is the parabola, or the quadratic formula, a parabola in x squared, anything that's the quadrature. You think of that in terms of quadrants, but it almost usually just means the square. And the quadratic, b squared minus 4ac, and these kinds of things in terms of these are the roots of the quadratic that we find. There's easy root finding in the quadratic, which makes it very tractable. And it builds the whole triangle inequality and all this kind of stuff. And it's very elementary in mensuration of all sorts. It's the foundation of Newton's method. It has to do with things like any kind of binary search, and which involves like pick a point halfway out. Is it above or below? Pick a point half in that. And so this is a very basic notion of binary search, where an array that's sorted can be searched for an item in logarithmic time, because if you have constant time random access to the elements. I mean, if the access isn't constant time for random access anyways, then it doesn't work. But in modern machine architectures, it's uniform or flat memory access, so that random access to a piece of memory in an unbounded array is constant time. So anyways, these sorts of algorithms and in the binary and for having and doubling and these kinds of things are very regular and usual. So what Pappus's theorem remind me about the quadratic sieve is that the quadratic sieve is kind of like that, except it's either arm of the parabola instead of this upper or lower line that makes Pappus's theorem. And then about where they cross in the middle is that they're very regular points on this and that. So it's kind of like thinking about taking something like, if it were possible to consider the transformation of the space of the branches of the quadratic form, the parabola, and figure out how they make straight lines, basically, and then to use that to show what the ratio and differences are between those and their integer points of those. And then what happens is that it's so that what's where they intersect is on this line in the middle. And so maybe that's just a trivial fact about that. Really, it's just that it's symmetrical about the axis on either side, the arms of y equals x squared. this parabola. one usually one often might write like y equals the root of x to draw it like the outward way, but here the upward way, kind of a way, horizontal or vertical. Here the point though is that the whether or not Pappus's theorem reflects something close and approximate and related to the quadratic sieve is something that I related from reading a bit out of Nernst and Nagel's, Nagel and Newman's proof on Goedel's consistency and this and that. So I thought that was pretty interesting. And another thing that it showed is what's called a dual to Pappus's theorem. And so what you do is you take any three lines that go to a point and any three lines that go to another point, and then draw the lines through those where they intersect, and they all point to a point. And so this was interesting to me. It didn't have a name though, so that's one thing that makes it kind of difficult to figure out sometimes. Is it Pappus's only dual to Pappus's theorem? One can imagine that there are other ones. One can imagine that there are things where contrived is they're parallel, or contrived the points are equidistant. Then they make the integer lattice and this and that kind of thing, where the idea is to figure out why that's so particular to only the 3 points on the 3 lines, or the 9 points in the 3, or the 9 lines in the 3 points, and how the ones are as collinear, those points, and the other is copunctal to the same point or on the same point, those lines. It was just an interesting thing when you might look up some more about Pappus's theorem, and that a lot of stuff that came into analytic geometry and algebraic geometry, it has that along the course. So I was looking at that the other day. Oh, there's one thing. The other day I was talking about third dimension vis-a-vis fourth dimension, and that it's difficult or impossible to visualize the fourth dimension. Why? Well, because visually and graphically, it does not really have there's not really like a fourth physical dimension. There's any variable you care to consider as an attribute or quantity associated to anything in space-time is totally, of course, obviously in a fourth mathematical dimension. But then the reason why it's so difficult to get up into 4 visual or graphical dimensions is because there's not such a thing. So anyways, what I said was that the optic nerve is the largest bundle of nerves, which is true, and then it goes right to the prefrontal cortex, which is right here in the brain. And then and I mentioned I wasn't too familiar with the atlas of the brain. So I went and studied it for a little while, and what I found is that the general notion is that the optical nerves come back from the eyes and they cross in what's called the optical chiasma, where they cross. And so that's a component, a factor of any animal pretty much with stereoscopic vision, 2 eyes, and then it uses it to compute things in terms of stereoscopic vision. And for range finding and parallax and peripheral parallax and this kind of stuff. And that's basically where that crosses is directly beneath the hypothalamus, which is the nerve center of the brain in a sense, or the hormone central of the brain with regards to all the messengers and stuff that arrive from that. So then the optical nerves proceed to the occipital visual cortex, which is in more of the back of the brain. The occipital is towards the back of the head, and so it's described that according to the theory these days of the atlas and the topology of the brain, or topography as you will, but usually it's just kind of called the atlas or the parts, that the occipital is in the back, and that's where the actual signal goes to arrive. But that's when it comes to like what that means for visualizing, because the point was for visualizing 3 dimensions and 4 dimensions and attaching them to mental models and constructs of objects, is that basically what is involved in terms of like the frontal forebrain and the midbrain and the rear brain, in terms of that sitting atop kind of like the cerebellum and the amygdala and in the older parts of the brain that are present in more lower animals, where as it kind of comes up and forward and over to the front, that's more the primates and humans have the most development in those parts of their brains. that what happens is there's about the back of the forebrain is there's these areas where there's many numbered areas or lettered and numbered areas in the brain. And so from the back, when the visual cortex is labeled like V1 through V5, these different regions, and they kind of identify them by different granularity or striatedness or other physical properties of the gray matter. Again, my vocabulary is loose and present, but not exact really in my brief studies of brain anatomy. And I never had one really open in front of me, in terms of that kind of thing. Some people's jobs is brain surgery, and so it's an important thing. Here that then these number parts are Brodmann's parts have the frontal cortex and the prefrontal cortex, which is where most of the executive function of the brain lives, including stuff like inhibitions and thinking things and the conscience efforts and things, is associated exactly with what controls the motion of the focus and direction of the eyes, with regards to how there's basically the unconscious direction of attention is according by the optics and what drives it the other way. And then there's that's where it's visualized things in 3 dimensions and 4 dimensions. So in a roundabout way, it's just making clear that it's part of its systemic consideration, where the last spot that the actual optic nerve ends is way at the back of the head. But that's not really where necessarily it's relevant that it goes. Then as with regards to its contribution in terms of, I don't know so much about axons and neurons and stuff like that, or the optic nerve bundle, but how it connects in terms of the optical chiasm and how that's kind of right beneath the hypothalamus and the thalamus is a pretty relevant thing to understanding mental models of vision, being largely the highest bandwidth sense of the sensory apparatus that there is. That what then goes into making relations for those of the abstract sense, this higher order or cognitive sense, where there's discussed phenomenology, and if the person can only conceive of what they feel by their feelings and their senses, the sensory, that then the idea is that this number sense and word sense and object sense are put in that category. And so that then when it comes to arguments of like Kant's and Hegel's and Descartes about, well, all I can relate to people is what they can feel, and because anyone who thinks can say that they don't think something, or along those lines, or in terms of mental models of animals, or an abstract stimulus response device, and the operant conditioning and this kind of stuff up into primates and animals with other higher order functions, including the symbolic and reasoning and language, which includes a wide variety of animals. If you think in terms of their modes of communication and modes, whether that's symbolic, but that is basically associated with mammals. But animals have brains. That in the humans, then it's kind of interesting that the development of the prefrontal cortex is about 6 times greater over the course of some evolution in Homo sapiens than any other animal. And so that, in terms of its exaggerated size, is kind of characteristic of the species. So anyways, I otherwise would want to correct that the optical nerve connects to the occipital brain and the visual cortex directly, but its influence is as of after the activation of cognition reflected in short-term memory in the prefrontal cortex, and the activations of cortex from this part up here about the activation of the memories, and these kinds of things which go into the overall function in terms of the regions and the parts and their organization and the activation of the alpha and beta waves, which are kind of linear, and the gamma and delta waves, which are kind of nonlinear, and the theories which go into various models of cognition. It was interesting to read this page about the brain also. It kind of details, like, have you heard of the left brain, right brain difference, and the difference between creativity and direct and linear thinking in terms of those two? And it's like, well, yeah, I've heard of that. And well, then there's various people have various levels of coordination between the two sides, and it has a lot to do between the left hemisphere and the right hemisphere are connected. It's like, okay, and it's like, well, actually, they kind of studied and figured out, and they figured that in terms of language, that nouns are on one side and verbs are on the other side. Oh, really? Yeah. One of those things is that if you ever hear somebody say, oh, really? Like you say something and they say, oh, really? It might be a tell that they believe it. They question it, but it's like, oh, really? So anyways, I noticed this thing when reading about Godel's paper, and that Nernst and Nagel's, or whatever it is Nernst and Newman's, Nagel and Newman's, book on Godel's theorem is pretty good. It phrases stuff in the language of modern model theory, and it's relevant about having an understanding of what the standard way of looking at Godel's theorems of incompleteness are. There was a footnote about Goedel, and it's like, he was talking about platonism, and platonism has been discussed here as whether there exist these ideals, whether they're the forms and that they exist independent of us. So when they was talking about Kant, Immanuel Kant, it's like, yes, that's what is like and so. And then with regards to usual apologetics about the deity in religions, it's that it's like, well, all that's reserved for the deity and the omnipotent and omnific and the omniscient and all such related notions of the absolute on high. That at the same time, those things are left their own place. So anyways, the footnote related that Goedel basically was a stronger form of Platonist, and so he's like, well, yeah, the Platonic ideals are independent of us. An apple is an apple, but the circular shape of an apple is an ideal, and one, the number or count of them is an ideal. And in a sense, words are ideal, and our words are non-logical, properly logical, proper. That he has further had a stronger opinion that is more of a strong Platonism. It's like, well, actually, the whole universe is a real mental construct of itself. And so then, what does that mean for us as thinking, feeling, sensing beings in a shared realm or the world in this universe? What it means is it's possible to approach the mathematical fabric of it and think of it in terms of universals. So when there's theory like physics is an open system and there's mathematical physics for all of an open system, it can be considered about that and those universals, and they're real. And so various consequences and considerations of it is like, well, how many universes are there? There's one. How big is it? It's infinite. And how about this Cantor space? Is it infinite and uncountable? What about looking at it the other way? Because then it'd be uncountable either way to each other side of the domain. It's like, well, then you make a square Cantor space, and this gets into the extraordinary. What does extraordinary mean? Well, ordinary means is by the ordinals. It's numbered. And so the numbers by the ordinals is that in the ordering, kind of as last time there was talk about the ordering and the vague fugue of the real numbers in the continuum, and about whether there can absolutely be ordering and this kind of stuff, is that instead that the ordinals, being these numbers of ordering and numbers, they actually live in a different theory than set theory, and they're called ordering theory. But anyways, in set theory, they're very primitive and ordinary mathematical objects. Ordinary in the usual sense of usual, and ordinary in the usual sense of standard, and ordinary in the usual sense of ordinal. Kind of like the regular and rulio and well-founded are associated as being the same kind of thing in this concept. So anyways, about the ordinary and the ordinals, the idea that there's the extraordinary is basically the same notion here as the non-standard or the extra standard or super standard or non-classical or extraordinary. And so when it was decided by Zermelo and Frankel, with the approbation of Russell, to add an axiom of well-foundedness that excluded all the rest of the universal relation except those that weren't Russell set, and if they were Russell set, we're going to call them something else and say they aren't, or the axiom of regular ordinary infinity, which is a restriction of comprehension, to complement the axiom of regularity, or well-foundedness, which is a restriction of comprehension. All the other axioms being logical and expansions of comprehension. Just that an expansion defines wider world of things. That an axiom that's in a restriction, in a sense, for some constructivists, is not acceptable as a true axiom. It's like, you can't deny that thing exists. It's just a structural feature of its place in the mathematical universe we were just talking about. So anyways, but it does keep things all ordinary and standard for a lot of the results that follow. And it's tractable in what it leaves fungible. And otherwise it involves this extraordinary. So the extraordinary, as we were talking about Kant's Ding an sich, this basically reflects that we inherited all this stuff from the ancient Greeks and the antiquarian, and that becomes classical. Then in the paleoclassical, which is kind of like in the paleo archaeology, exploring the ancients, or what it is, the retroclassical, retro-superclassical, is to consider these ideas that would be this about the completions or the infinity or Zeno's arguments and this and that. But for Kant and the Ding an sich and the monadology, it's all these things that would otherwise be the paradoxes that were discovered, that after thinking things over and making things abstract and pondering the existence of God and trying to figure out what was these ultimate notions, what came from nothing, and then what happens when that's the same thing as everything, and what happened when all the complementary duals reverse because, for example, it's a universal group of them, that this extraordinary is just the notion of that which lives in the universe which transcends itself, which makes it so that infinity contains itself, the universe contains itself. The order type of all ordinals, when you collect ordinals in a set theory to make ordinals, the order type of all ordinals is an ordinal, and its name is ord. And it's extraordinary. It's not a set in all set theory that's regular and well-founded. It's a set as it lives in a class theory, when there's class set distinction, that is a set theory. Set theory was broken, so they introduced another name for groups called class, and that's what they use to describe set and class theory together. It's a proper class, according to how Quine puts it, an ultimate class, that as an object in otherwise a universe of expansion and comprehension, it's a prototype of an extraordinary object. And then in terms of all the universals and nulls that live together and whose two sides basically are constantly alternating and reflect that out of that arises all what's matters of regular form and structure, and in the middle, our place, the mesoscale, in the middle, that it's not such an unusual thing. So yeah, the quadratic, sieve, and Pappus, and reading in this book, and that Goedel was a stronger Platonist. Then and then about, well, then how can we address Goedel? And it says the theorem is incomplete. How can this theory that have a universe, our theory is incomplete? Well, if the universe is a theory, this is the idea that there's the extension that who made who, the universe or the thinker. Well, then the usual idea is that two thinkers can at least make a little universe together. But then in terms of the objective person and the universe of the objective person, the idea of this strong mathematical Platonism ends up arising that, well, how can that be complete if Goedel proved that his theory is strong enough to support arithmetic, which she first showed complete or closed, that there's no upper bound, there's no like highest finite number according to theory, prove that part. That the incompleteness that arrives at is that there are theorems about objects that are not part of the theory. And so there's both true things about the objects of theory, and there's true things about some theorems of the theory that would be part of a different theory. Whatever could be independent of that theory. Then the idea is, and as to whether, well, once you have a theory of axiomatics, you can't really restrict comprehension on it anymore, because that would remove or invalidate at least some of the theorems in the theory. And then if you add an expansion to comprehension, the idea goes, then that would change the axiomatics of theory. The axioms of the ZF, Zermelo-Fraenkel set theory are very well chosen and very well reflect a lot of work that goes into for these objects, that they have enough fundamental structure to reflect all this axiomatic set theory, descriptive set theory, descriptive dynamics, mathematical theory up above as a foundation. But this extraordinary and the incomplete then arises as how they can be so. So in the Nagel and Newman's book on Goedel, they also reflect on a point that Goedel's opinion was that there was various ways to look at how it could be that the theory could be finitistic, he called it, but written out so that incompleteness would not result. So it's kind of underdefined what he meant by that, but my opinion of it is this. If you have a theory with all axioms, like a universally axiomatized set, that the first principle is that all the final causes are facts, or if you can derive at and devise at the theory that is from no axioms, that either this null axiom theory or universally axiomatized theory can be the same thing, that you can still have a complete arithmetic, and Gödel's incompleteness theorems don't apply. And what were otherwise his results about that there exist theorems about objects that are not defined, instead has that they prove that the door is open to outside of this theory to look at this singularity theories as multiplicity theories, to have what would result then how these things could be that there's independence of other related theories in this overall extraordinary, but and only to be replete in a more geometric and continuous sense. This is besides the fact that any theory can be inconsistent or not concrete. The idea is that for a strong platonism, that a theory is constant, consistent, complete, and concrete, those being the desiderata and requirements of a theory of everything, presumably one theory of everything, singular, definite, the definite article, is that that's kind of how I look at it, and that's also how other people look at it. And then it's called anti-foundational set theory, or non-well-founded, or here it's called extraordinary, and extraordinary is not an unusual term too. Over the course of time of development, these same concepts are called different things. Like the axiom of choice is called Zorn's lemma, or Ono, O-N-O, from a Japanese fellow, and the well-ordering principle. And it's just an example that they're the same concept in terms of these other concepts, that the set class distinction is in a sense artificial, because what's a class of geese? It's geese. What's the set of geese? It's also geese, G-E-S, geese, the birds, the flying animals. Sets and classes are the same thing until such time as what went into restriction and comprehension to reduce the comprehension of the quantifier comprehension, to a restricted fragment, a bounded fragment of otherwise this more extraordinary universe, that those are why they had to introduce a separate word. because that's how it is, and because otherwise you'd be talking about universal objects, and objects, a theory with an elementary primary object in it, and so this is called something like the primary object of the theory for logic and philosophy, and it's very closely related with such explorations in the technical philosophy as Kant's on Zig. Well, now I wanted to talk about Pappus's theorem, plural, Pappus's theorem, and the quadratic sieve, and then I was going to frame that in terms of the quadrant of the identity dimension, and how that makes it so to consider that it folds in and folds out about it, that it makes kind of a way to look at Pappus's theorem as the xy axes of the identity dimension and the line they draw together in the middle, then to start figuring out how that would be what would be the scaling to make it so that the quadratic sieve would be related to it in terms of three collinear points, and then in terms of this dual, these three copunctal points, that then coming back roundabout, it was to get back into this consideration of the geometric mean and the harmonic mean and the arithmetic mean. A discussion for last time as about the relations of the discrete and the mean, median, and mode, or those statistics, and the arithmetic, harmonic, and geometric mean, and then what gets into the concept of root mean square. What is root square? Well, if you take the root and square it, it's identity. Square and root are inverse operations. So what's root mean square, RMS? It's a concept from figuring out how to compute things in electrical flow. It's like, well, we're going to use a method, and it's kind of like the intermediate value theorem, or it's kind of like the mean value theorem, and we don't really have a way to say that these discrete things add up to not an infinite thing. And so we're going to take their mean, we're going to take the root and then take the mean of that and then put it back into the square. And then the number we get out of it is quite sensible. And so it's related to this arithmetic and then the geometric and the harmonic means. So let's see because Kazarinoff says about arithmetic, geometric, and harmonic mean. So far he's gotten to the definition of what is a greater than 0. It's positive, and it's a greater than 0. The algebraic operations of addition and multiplication have geometric interpretations on the line. And so this is that if you have a line, if you have two lines that are distance 1 apart, then if you have a number line and they're negative x, 0, and x, then you want to multiply them by 4. You can just draw a line with a slope that's four times as much as that's the parametric form, with an angle that's 1/4 of the perpendicular angle with regards to directly beneath that line. On a copy of it, it would be marked the same value. X times 1 is x. So if you consider two lines and you have one directly beneath the other one, you can draw a line from one to the other one and say anything times 1 is exactly what's beneath it on the line. And then thinking about positive, negative, and symmetrical, you can take half that angle and draw that connecting these two lines separated by distance 1, and x will connect to 2x, and 2x will connect to 4x, and all this kind of stuff. And any number on the line will connect to any number on the other line. And it's inverse, so this way. Then in order to perform the operation of addition by 4, for example, we slide the real line to the right 4 units. So this is basically a similar notion as that the product exists, that the differences in the scale or the ordering exists. Or the indexicality, the index exists. So when you think about the natural numbers, they're the whole integers, the counting numbers, they're as zeros sometimes included, 1, 2, 3, 4, 5, dot, dot, dot. And then there's various ways to make models of them. There's simpler and less simple ones. And then the idea is that the simple ones include only an inductive set. They don't even necessarily include the modularity and relations and the ability to take two of them in the model without having to backtrack and build a whole nother model of the action and operation and counting, whether the model also has an arithmetization and a geometrization, which results that when you look at it back and forth, like a slide rule, that it results that the computation is automatic or constant time because the structural things all change together at the same time. Now, whether that's more simple or less simple is kind of more simple when you think about how it models the operations is figured out this way. But it's not necessarily so as it doesn't necessarily apply to only the properties that you expect of the whole numbers, the counting numbers, the integers, and the natural integers. And as to why they have various names for these same things is in the contexts where they have different properties as to how they're arrived at and where they can be arrived from without further ado, relating them to all the things by their real values in any sense of the geometry's integer lattice. But so then he describes this and says definition. A greater than B if and only if A minus B is greater than 0. So he defined subtraction. He defined A greater than 0, and now he's defined if A minus B is greater than 0, then A greater than B. Then he notes that according to trichotomy, and so there, as we were talking about last time, there are other definitions that will fulfill keeping it so. These properties that arrive at are so. And so the associative, commutative, distributive, and transitive properties, according to the operations of the laws of arithmetic, are great because when they're closed and the properties exist, they map to the same properties in the algebras by the quantities. So inequalities are transitive in the real numbers. A greater than B, B greater than C implies A greater than C. Transitive. If A greater than B and C greater than or equal to D, then A plus C is greater than B plus D. So this is kind of a distributive property as far as. But what it entails is that because A is less than B and C is less than D, that A plus C, the contribution from A is less than the contribution from B, and the contribution from C is less than the contribution from D. That otherwise they're scalar linear terms. Again, you can see any number of ways to write how this theorem is proved, and then that this is used as a fact. And then what does he have here? He has A greater than B greater than 0, C greater than D greater than 0. A C greater than BD. And again, this is making use of basic properties that you just see in the vector field. That the AC greater than BD, because again the contributions are so the products would maintain the so. You can establish a delta epsilonics rule, and it's like, well, if this and that were so. You can establish various kinds of ways about the inverses. The 1 over A is less than 1 over B because it's the inverse in the operation. That seems a definition. I'd like to see how he defines that. So what he does is he introduces a constant h and k, and then he says they hold so, and then they would be so for like this and that, and that's like so. And then for the second conclusion, oh, he introduced one. He introduced the quantity 1/b, and then by multiplying and then carrying out the multiplication of it out, and then the b's cancel, then he's left with a in terms of 1/b greater than 1/a in terms of the just this quantity he introduced is just an arbitrary quantity, and then noting that using the properties of algebra that cancels, it has an inverse, and in this case the inverse is reciprocal. And so, according to algebra, inverse and its reciprocal, their product is identity. So that's how I did that. It says, before we state the next theorem, let us review the definition of a positive number raised to a fractional power. A number raised to a fractional power, which is the fraction as numerator or denominator, is the nth power and the dth root. Now, I wanted to, I wish I knew more about the increment, addition, multiplication, powers, exponents. And why I'm curious about this, and maybe it's clear to a lot of people, is that when I think about then the terms as applied to them, it's like increment by 5, it's plus 5. Addition by 5, it's plus 5. Multiply by 5, it's addition of the same object to itself so many times. So addition almost kind of sticks out in the middle, because you got increment, multiplication, powers, and exponents. Now, what do I mean by this? It's like, well, yeah, when we talk about addition, we just add two numbers. Well, think of it first as that increment is not addition, but it can be accomplished a given number of times. So increment 5 is just to increment 5 times, and multiplied 5 is to add an object to itself 5 times. And 5, let's see, 5, 2, 5, power 5 is multiply multiply the number itself again in time. See, now it's added not only a term in terms of the previous operation as a constant that's the same constant, it's the same addition formula, or otherwise the same value that comes down the constant, but then it brings in also the second number, which is the value itself as it scales up and scales in. And so exponent then is kind of the same way. It's like, well, now take this number and multiply it by itself so many times. So why I'm taking this brief foray into a deconstructive account of the operations of addition and multiplication and after increment and before powers and roots, powers and exponents, with at least some of their relevant inverses, the logarithms and roots and additive inverses and previous numbers, that these are the kinds of things that I want to figure out in terms of the apparatus, how to define them in terms of things on a line. So if we can figure out how to make a linearization of that and bring that on down in the way, first of all, that is very familiar to anybody who knows like the addition formula of laws, computing products of exponents and powers by summing the terms, the operands here, but the powers. I've forgotten what exponents. The exponent is here the operand. Okay, I forgot what the name of the base part of it was, but it has one. So, anyways, that's all familiar as laws that make addition formula. The idea is to have for these addition formula and all this kind of stuff that makes things very tractable, and possible to compute with a stroke, which would otherwise take a whole page or so of things. Why, the famous story of the kid who added up all the numbers between 1 and 100 by adding up 1 and 100 and multiplying it by 50. And the idea to try and figure out how to get something like that going to compute something like the factorial or gamma function, as Hadamard and Stirling and I do somehow. These are the kinds of things that make for a brief foray into a deconstructive account, and also help to think about that in terms of the operator calculus, because that's kind of what the operator calculus affords. And similarly, when you have differentials and integrals, or the prederivatives and the antiderivatives and the differentials or the differences, is that those relate in the rank and order how many times they're applied. And then when they have those integer orders, it's one thing, it's simple. Like the factorial is 9 times 8 times 7 times ... for 9 factorial, 9 bang. Where the gamma function is defined also on the non-integer parts. All the numbers for the fractional inputs. So here, let's go back to what the author was talking about, defining powers of fractional, powers of positive integers in fractional terms. I've noticed that the YouTube thing will, when it's trying to pick a cover page or photo for a video, what it will do is it will scan until it detects what it thinks is a smile. And it's funny because I don't tend to show my teeth necessarily all the time when I smile, but when I do, it's more of a grimace. And so I think that it's trained on a model of what it thinks is what has been called smiles, which are fake. So anyways, since P is rational and positive, P may be written as M over N. So here, where do we go here? And let's see. Let P be a positive rational number and let A be a positive rational number. Real number. So P is rational and A is real. And a number is rational, can be written as M over N here instead of N over D. Since P is rational and positive, P may be written as M over N. All right. The symbol A to the M is defined to mean M many times, its product taken together. The symbol A equals 1 over N stands for the positive real number such that X to the N equals A. So it's called, usually called the root. But in algebra, it lives in this setting. So are we going to say, well, why do you care that there's no difference between arithmetic and algebra in terms of roots and the existence of this inverse by this thing? Isn't it neater, easier shorthand in the assignment to leave it in algebra's world? Isn't it closed? Isn't that enough? ... Why do you care? It's like, well, because on the outside there's either side of the ridge, and it's free to come and go as it pleases, and I care because it might not, and so I want to know, and then I'm happy to figure out how and leave it so that it's closed, and understand that all the models that's its strength and its weakness, and then that it follows the course and stays aligned and does all these things that's expected of it, and then when it doesn't, I'd like to have an idea what happens instead of undefined behavior. What's undefined behavior, you ask? I don't know. Moreover, A to the quantity M over N equals quantity A to the M to the 1 over N. When I read these things, I just try and reflect that quantity is kind of like quote. So it's like reading words and say when you say quote and end quote, it's just like whenever you say quantity, and when you say quantity again, it means end the previous time quantity. And so it would quantity open or quantity close. Almost all the times these notations in the reading and the bracketing, according to the precedence, according to the quantities, as to how they can be written on one line with various typographical signatures above and below and left and right and in either corners, usually not in the front corners. Everything kind of flows left to right. That here is for a matter of reading the thing, which is already graphically, visually in the typeset of the thing, and for a little language that. So when in some of these previous talks where there's lots of quantities and this and that, I'm especially reminded of the Mulgans, nonlinear electromechanical effects and applications, or the Fourier style analysis stuff, or the some of the path integral stuff. That was more conceptual and descriptive. But when the quantities are all these algebraic quantities and properties, that's kind of how it's read. And then when the letters and numbers are the same but upper and lower case, I'll usually just ignore that. But then only when they're in the same formula, say big and little or something like that, or Latin and Greek. Everything is Latin. It's called Latin 1 is our code page. And it happens to be the same as the keyboard. And so then other alphabets are primarily Greek because this is a technical alphabet in terms of the symbology, and of course it's associated with the derivations historically. And then variously borrowings from other alphabets, the symbology. Then sometimes there are small words or abbreviations or short forms for words. Lim for limit, S.T for such that thus it is so. Without loss of generality is with WLOG. These are to be avoided. Well, WLOG is to be avoided, but such that is very clear. It's just a form, and lim is everywhere. Let me see. What are some other usual words you'll see here? Mostly lim. Lim for limit is probably the most usual little word, because then otherwise there's just integrals and differentiations, their notation, and Excuse me, I'm boring sometimes. If q is a negative rational number, say q equals negative p, where p is positive, then a to the q equals 1 over a to the q. A to the q equals 1 over a to the p. So before I was describing the fractions of the part, and so the numerator and the denominator, and then in terms of the negative, it's as of the inverse of that number. The negative power is the inverse of the numbers. So thinking back to this little hierarchy of increment, then, and that's addition, and then multiplication, and then powers, and whether that should be like increment and multiplication into powers, and then exponent, potentiation. The idea I've been just having for a while now, but mostly just talking it out right here, is to try and figure out what pieces of those make up for then these parts like so have these alternate little alternations than what's otherwise kind of this bracketing that makes it so impossible to express these things about their roots and their inverses. And it's saying, okay, now the products in terms of the positive negative are like this and like in that and so. And so the idea is to keep things simple is to try and make that up in what's framed as this identity dimension, where the function is a straight line f of x equals x, and only the positive numbers, and with all these things that's been going on in that space, then to figure out for the operations that are fundamentally addition and on outwards from that, and the derived operations from addition, is that in this deconstructive account of addition and division is separate in the arithmetic, because one is essentially bringing together, and the other one's essentially dividing apart. And so to think of that otherwise, it's like, well, let's finally just end up having that there's multiplication after division, but there's powers, and there's exponents. Why don't those live in our arithmetic? Because our adders and multipliers work on these, say. That's fair. They're formal for the handles they have, what levers they provide, that for the inputs that people have, that those are the tools that they are and they use. It's fine. But why not? Otherwise, think it over and think it out that really natures say, or there's somebody who's got like, I can divide or I can add. And so I'll implement all my arithmetic in terms of that. And so then when I have to figure out things that are these odd or fractional values, sometimes it might be very contrived, or I'll have to work at it much longer, and you end up with long subtraction, say. In terms of what's the trade-off and the compromise and the representations of these things, what are numbers, and what are the digits we write, and what are the operations we expect and know to be closed on them to be so. These are kinds of things that get into helping understand. For me, I feel like I have a deeper appreciation of the forms that they can take, the rules that they follow, the abilities that I or anybody else has to carry out to make a shared common lexicon and terminology and definitions about them, that it still results that there are more levers that one can activate. And correspondingly, that there are more levers that can activate closures, in terms of then finding more addition formula, because then you can amaze your friends by adding up an infinity of numbers before they get one, which is kind of amusing, like calculus or something. So a to a negative number is 1 over a to that positive number. It's inverse. It's the inverse to the inverse. Trying to figure out that in terms of these things is, where does it reflect that this kind of even an odd rule would build up an operator calculus, so that if you know these abstract operations were carried out according to the things that connect them together by these and those, that they would make it like so. Excuse me, I'm gesticulating a bit too much and taking advantage of the scale of the camera, but that's kind of the idea, and I feel like it's a little bit lacking in the presentation, because maybe just because I'm unfamiliar with it, and it's usual in other places, and very usual, regular. If there's an operation past exponentiation, they call it tetration often. It's like 2 double arrows. It's taken to the power. It's just squaring that. In operator calculus it lives. Of course, he says a to the 0 equals 1. It's a definition. It's an axiom. Because 0 equals 0. I always try to be a grandiose hedge. And I only trust other people who are also in terms of mathematical and theoretical things. In this book, we shall never have occasion to consider any number raised to an irrational power. However, for the sake of generality, we state the next theorem without restricting p to be rational. Problem of deciding whether such numbers as root 2 to the root 2 or pi to the pi are rational or irrational, once they have been defined, is of great difficulty. There's continued fractions. They're kind of difficult. I don't really get them, but they're a form of taking what's a long operation and the ability to make representative things. So they must make other things short, like some kind of tooling that's basically grinding out in the box, some kind of box thing, or like the yenri. It's a similar type of thing via the exchange of what is long or involved in time coordinates in the one. It can happen what is at least, it can be imprecise in the other, trading precision for time. But here about there's also then for definitions of irrational numbers, like the classes of irrational numbers. Then there's something like Apéry's constant. And it's like, well, what is that? It's like, well, it's a series of rational numbers that sums up to an irrational number. It's like, well, there's lots of series of rational numbers that sum up to rational numbers. But it's like, but yeah, these are all rationals. So these are the kinds of things to kind of figure out. A priori constants. So here the author then though just kind of describes that he's like, we're going to call this complete and say that it interpolates perfectly between them. Theorem, he says, if a greater than b greater than 0, and if p greater than 0, then a to the p is greater than b to the p. If p less than 0, then a to the p is less than b to the p. So he's now, we started yesterday, we ended yesterday with a greater than 0. And so then today we've got to a squared greater than b squared. And also including notions of, for the usual operations of roots and powers in positive roots and positive powers and negative powers. And for positive numbers and negative numbers, that inequalities are like so, and thus they have maintained these properties of the transitivity of either way, and the switches, the inversions, how this operations hold, and their relations, left-hand side R for relation, right-hand side. This is the notion of the binary or two-place or dyadic relation. So that's established. Also, a cubed greater than b cubed, and da, da, da. Well, all right. And then he gets into some notions about computation of roots, and so he's talking about roots. And so then the idea here is to understand what is the geometric mean, the harmonic mean, and the arithmetic mean, where everybody knows what the arithmetic mean is as an average. And then the idea is to understand what the geometric mean, harmonic mean, and the root mean square is and why for phase and it usually in its terms in the signals. And so then what was discussed and discovered was a brief range over some things about Pappus's theorem and one of its duals, as it's so called, and it's to be reflected on what and how that reflects why it is what it means. I want to figure out how that, if it does, connects to the quadratic sieve. And then there's some notions about peripherally about the structure of thinking and the visualization of the 3 and 4D and its symbolic meaning in words, and how it's easy to string out 1,000 variables and call that 1,000 dimensions abstractly. And with regards to what shape it has, then is determined by these sorts of definitions, the operations in the operator calculus, and make it possible that for all the items you can establish it so and works its way on out. Get it sensible, get it fungible, make it tractable, get it out. These are the kinds of things. And then some just usual discussions about all of the extraordinary in theory and why that class set distinction is a thing and why it shouldn't be. And all these kinds of things, and the ordinary and ordinals and extraordinary, and back down to integers and talking about the numbers. So I hope you have a great day. These talks are about an hour, at which point the video becomes a file larger than 4 gigabytes, and it results in that it does not fit on my old 32-bit file system anymore, where 2 to the 31 and minus, or 2 to the 32 minus 1, or 2 to the 31, 2 gigabytes or 4 gigabytes. The size, unsigned, is usually reflects an implementation detail that is quite a large number. All right, anyways, hey, have a great day. I hope this fits.